Assalamualaikum. Bismillahirrahmanirrahim. Yes, hello everyone. So this is CHENG465 Chemical Process Safety. Today we're going to be talking about source models, and we want to look at what does the source model mean, and what exactly where are we standing in our chapters now. So we have taken the threshold limit value, and of course we have taken some kind of questions to know if we are exceeding those threshold limit values or not, and what ventilation flow rate do we need depending on what mass flow rate is literally dispersing. And based on of this, we want to study the source models. It will be clear just in 2 slides from now. But to study the source models, what we are trying to say here is that, well, many of the accidents happens in our life is because of toxic, flammable, and explosive material. But how do these toxic, flammable, explosive materials, they go out into the environment or into the atmosphere? It's because of the spills. So what do we have? We have spills, leaks, and these spills or leaks happens because of holes. And this hose could be in tanks or it could be in pipes, right? And we are talking about holes, or there could be holes or could be cracks, right? And talking about that, we need to study if we have a certain hole, how fast it's going to be spreading out. Okay, so if you're talking about this pressure of a fire extinguisher or to put a fire, right? So there's a certain energy that is going out here that is flashing or spilling out. If you're considering that this is not like a fire extinguisher, if you consider this like a real spill of a toxic material, right? How much amount you're going to lose to the atmosphere or to out of our system, right? How much you're going to lose. So this is what you're trying to study here. And looking at, just to have a look of what we have here, what we had taken in chapter 2 and chapter 3 is, for example, we were calculating through the responses that we have and through the probit model about the number of deaths or number of people who are getting affected by having something hazard or toxic to their ear or to their nose, to their lungs or to their hemorrhage, nazif dakhili, or something that could happen to their eardrums. So we calculate here, okay, so some kind of a damage that happens to the property or to the people. So all those of these damages or toxic substances that have a threshold limit values, we studied that in chapter 2 and 3. All right, and we consider calculating the QM and the CPPM. All that is in chapter 2 and 3. Well, now the question is that what is being dispersed? It comes because of what? It becomes of a certain hole in a tank, and because of this hole in the tank, I have this dispersion of material that I need to calculate if it exceeds the threshold limit value or not, right? And now this whole of the tank, I may study into more details the type of the pipes that I want to develop, so that I don't have this frequent holes or cracks in my tank or pipes. And if I do have them, they will spread. How far they will go, we need to talk about chapter 5 and what are the areas that will be affected. Now, if it's flammable or toxic, when we said toxic, we studied the probit model, the TLV. However, if it's flammable, there are also some flammable limits that you're going to study in chapter 6, and then in chapter 7, how to fight or defend these fires and explosions. And later in chapter 8 and 9, we are going to study the relief sizing, and then if you want to study how toxic is this, if you want to use a checklist and discover what toxic substances we have in our plant, that is chapter 10. And then taking the mitigation factors, that means how do we escape, what are the measures to response, where's the place that we have high risk, that is in chapter 11. Okay, so I hope that was clear. So this is a kind of an example of a spill. maybe on a Google map or whatever, if you can look at it, that's a small thing here, but that's big, by the way. That's really from a very high place. So you see how much amount of the spill of oil. And that spill of oil, it could have taken hours, it could have taken days, right? It depends on the hole of that in the tank that caused that big spill that I have, right? So what you're talking about the spill due to a break in a pipeline, due to a hole in a tank, a runaway reaction that caused this kind of a spill. And continuing, that spill that we have, it could be in a different form. It could be a liquid, as we had shown, or it could be a gas. And you see this gas spilling out from this pipe that we have here, and how much of gas that we are losing. And if this was listed toxic or a poisonous gas, how much that will affect the people who are living in that area, and how much is going to be spreading. So simply what you're trying to hear is say here, in this chapter, we want to study the dispersion model. The dispersion model. How much is being dispersed? How much is being dispersed? We want to calculate the mass flow rate, the amount that's being dispersed per time. And in this case, we can calculate how much liquid is being dispersed per time, or how much gas is being dispersed in time. And actually, the amount of liquid being dispersed, if it was a hole in a pipe or a hole in a tank, would be different. Or the amount of the gas being dispersed, if it was a hole in a pipe or a hole in a tank, will be different, right? So all of that is part of what you are trying to study here. And definitely what you're going to getting into our system, that this gas or liquid, it may have an effect on people or property, or of course it could have an effect on the environment. Okay, so let's start. And starting, we are going to start with the introduction to source models. So we said we are going to study the source models, and starting with the source models, what do we mean here? We want to study the source models if we have a hole and a crack in tanks and pipes, or leaks in flanges. Flanges, like you're having two pipes and you're sticking these two pipes together, okay? Or you have a leak in a pump or a valve, or you have a ruptured pipe, okay? So all of those situations, how can we decide what are the models? What are the models that we can use here? What are the models? And of course, we can also study the relief system, but that's not part of this chapter. And if you look at this system here, we could have a crack in the tank. So this is a big tank, right? This is the tank. That is a tank that I have here. And within this tank, I could have a hole within the tank, or I could have a small crack in that tank, or I could have a problem with this pipe connection where there's a leak here. Or I could have a hole in this pipe, or I could have a crack in that pipe, or it could be in the valve or the flange that is connecting these two pipes. Of course, you will not have all of these problems in one time. It's impossible, right? So imagine that you went to the tank in your first days, and you have a hole, a crack, and a hole, and a crack, and a pipe, and a tank, and oh my God, what's going on? My advice to you is to run away. Okay, I don't mean that to run away, because this is like a disaster. It can never happen, all of them at one time. It could only happen, I don't know for one, but if there's going to be a blow in that big tank, and there's a big disaster is going to happen. It never happens like that, okay? Don't worry. So we're going to study, if there's a hole in a tank, what will be the QM? If there's a crack in a tank, what will be the QM? Or a crack in a pipe, what is that QM? Or a crack in a tank, what will be that QM? So we are going to study those mass flow rates. Now, there's a lot of derivation to obtain these values, okay? So we need to do like mechanical energy balances to obtain the equations. We are not really concerned with the derivation flow here, more than we are concerned about the final equations, okay? The final equations, and you understand those equations. All right? So what do we have here? So we're going to show a figure here in a moment that for gases, vapors, and for liquids that are within a process. So for example, I have a tank here that has only gas. So I would expect that only gas will flow out. I have a liquid. Of course, with the liquid, you have also gas here. And of course, you're going to have a vapor of that liquid based on the vapor pressure that is sitting here up. And I'm going to have a leak. For example, there was a crack. So I'm going to have a leak of both vapor and liquid, which is possible, depending on that it's pressurized here, right? Where it may flash here as well. Or I could have a leak that there's a liquid leak flashing into vapor or liquid here. So this could be like a two vapor phase, or it could be one phase. And that sometimes making it two phases, or not making it. It happens that the two phase becomes more difficult to develop a model for that. Now the small liquid droplets that gets out because of flashing, for example, like a spray, where liquid goes out from high pressure to very low pressure, so it becomes a gas. These small liquid droplets of a spray or a flash, we call them aerosols, okay? We call them aerosols. So they come from a flash stream, and of course, they could be taken by a wind current. And if you take wind current, it goes to another area or village or a city, which could cause a problem if it's toxic. A leak in the vapor phase above the liquid can result in either a vapor stream or a two-phase stream. So this is simply explaining what I just explained, that if it was under pressure, there was a leak, that liquid could become vapor. Okay, so what we want to study in this chapter here, we want to study a flow of liquid through a hole, a flow of liquid through a hole in a tank, a flow of liquid through pipes. And then after we finish with liquids, we want to study a flow of vapor through holes. We will not take flow of gases through pipes. It's very deep into the mechanical engineering balances. Could be very complicated and straying us from the safety ideas. Flashing liquids are going to be also taken, liquid pool, evaporation, or boiling. So we may concentrate mainly on this one. The last two ones are I will see that how much time do we have to cover them or not. But the main source models that I would like to cover are these four. These are two simple ones. I mean, we can't take them. Okay, so talking about the flow of liquid through a hole. So if we have a hole, okay, there's a hole and it's spilling out. Now this pipe is like a sharp edged. And why did I say a sharp edge? Because something is going to come on the way to tell us if there's a high friction or a low friction here. So there's a friction, of course, of this gas getting out here. Well, if you want to do a balance between this point here and that point there, where we have here a certain pressure inside the tank or the pipe, and we have a certain distance. Of course, the distance here, both of them are the same distance. So we are going to consider them that delta Z is equal to 0. And of course, pH is up. This is a certain within a certain pressure inside the pipe, right? And this is like the atmosphere. And of course, if this is open to the atmosphere, this is P atmosphere. And so how do we do a mass in mechanical engineering balance? This is the mechanical engineering balance equation. So you're going to start from here. So now, what are the terms? The terms we have here is dP, which is the pressure, change in the pressure, and rho is the density, U is the velocity, Gc is just the constant of the gravity. This is the gravity, and that is the change of the height over the datum. That is the friction loss. We call it the net friction loss because it is like it is a sum of many friction losses. So this friction loss could be because of the entrance, or it could be of the exit, or it could be more than that. And then we have a shaft work, okay, shaft work, and that is the mass flow rate, okay, m dot. So the one that we would like to calculate. So this is what we have in our terms. In this case, what do we have? If we have our system, the first thing, because it's an incompressible fluid, we could consider that dP is equal to delta P, just to make things easier. And this is what I said, that if you have like a pipe, okay, this is like the inside of this pipe, this is the exit of that pipe, or this is a tank, this is the exit of that tank. A generic form for any hole that we have for a system is going to be this equation here. It's going to be this equation here. So now what you need to know? You need to know the equation. You need to know the equation. And that Qm is a function of what? It is a function of a friction term here, which is C naught. It's a function of the density, and it's a function of the gravitational constant and the gauge pressure. Great. So more pressure, gauge pressure, will push out more fluid out, which is more mass flow rate, right? And if I have this less friction, or so this is like 0.61, for example, so I'll have less going out. If I consider that as 1, so like this is the maximum flow rate going out. Okay, so what do we have here? So this system tells me that I have a certain pressure within the tank, a velocity which is 0 here, especially if you compare it to an average velocity outside this term. Delta Z here from this point to this point 0. There's no shaft work. Here I would consider that it's not really accurate to say I have an average velocity. So what did we do? We added a term, and actually it's hidden in the C naught term. Okay, it's hidden in the C naught term. I don't know if you have seen this alpha term. I did not explain. So it is a correction factor. And that correction factor is very important because it helps us to correct things that if they become away from their true value. Okay, so that is the equation that I want to know. Can you tell us, please give us an idea about how did you derive or get this equation? Some of you would ask that question. And other students would say, oh my God, why are you asking this question? I mean, we have one equation, just substitute and that's it. Okay, so just if you like me to answer that question, I would say that you would go to what? Your mechanical engineering, mechanical energy balance, in which we said that this dP over rho becomes delta P over rho. And mu, we're going to substitute this equation for velocity for u. The delta Z is 0. And no shaft work 0. So all what we have is now is to rearrange this equation, rearranging it in a way that we have this. We have an equation, and this equation in which I'm going to have this very beautiful equation for the velocity. And if you just multiply the velocity with area and density, you're going to get the mass flow rate. And here we just named a new discharge coefficient, which we had two coefficients to do with the friction and the correction factor. We just made them as one constant. All what you need to know is that we get this final mass flow rate of the total mass spilled. Okay, the total mass spilled. Now, if you look at this equation, what do we have? We have the area of the tank, we have we know the density, we know the GC, and we know the pressure inside that tank, but we don't know C naught. We don't know C naught. How to know C naught? Okay. Other than that, what I want to mention is that so these two equations are very important to know. These two equations. So please note them. Please note them, because sometimes you're given the velocity, average velocity, and by knowing the average velocity, you can find the QM term. So you need to know these two equations. Okay, so we said that C naught. I don't know C naught. What is C naught? So what is C naught? C naught depends on several experience. Okay, let me say it comes from experience. I can calculate it, by the way. I can calculate it, but sometimes it's very complicated. And getting away from this complication, I make life easier. How to make life easier? C naught is equal to 0.61 if it is a sharp edge orifice and Reynolds number is greater than 30,000. C naught is equal to 1 if I have well-rounded nozzle. C naught is equal to 0.81 if my length diameter ratio is less than 3. And if I don't know, I'm not certain about what I'm dealing with, just take the maximum C naught. C naught is equal to 1. And what does C naught is equal to 1? If you substitute C naught is equal to 1 here, it means that I will have the maximum spill. So I'm taking more safety precautions by taking into consideration that all of my mass, or I'm taking the maximum flow rate that will go out. But if you take, for example, this as C naught as 0.6, so you're considering some friction that prevents some of that mass to be spilled out. Okay, but if you're not certain, you're not clear, consider that this as equal to 1 to be on the safe side. Okay, so that was flow of liquid through a hole generally. But if you want to look at the flow of liquid through a hole in a tank, okay, so that will be similar. That will be similar to what we were talking about, and that will be this equation. Oh, come on. You said that will be similar. The similar of the idea, there's PG and there's P atmospheric outside. But the problem here that when you have spill, the problem here is that the height is going down. It's going down here, right? It's going down. And as it goes down and lower, as lower the height goes, you have less head pressure and you have less, what? Less spill. That means the QM here will be changing depending on what? Depending on the height. Depending on the height. Which means I need to do the mass balance for DHL by DT. Okay, so did you see here? That is why for a tank it will be different. You need to know this equation, but the question is again, how did you get this equation? This is the derivation. Well, I have the mechanical engineering equation, the mechanical energy equation, and my velocity is a function of what I have here. There is a way of how to prove this. And the instantaneous flow rate that I will get, this is the instantaneous flow rate. I'm very happy I got the instantaneous flow rate. But come on, QM changes with time. QM changes with time. This changes with time. And because it changes with time, we need to find DHL by DT. And then we integrate to find HL. And of course, HL is going to be substituted here so that we can find QM. So that is the idea. So how to find DHL by DT? If you can remember the dm by dt equation, I will not go through that in details, but the simple thing that I can mention here is that the amount that goes less, it is spilled out. This amount that went less is exactly the same amount that went out, which means that the amount that went out, it is the change in the mass. And that is why you have dm by dt is equal to minus qm. And I already have qm. And my m is what? Is density into volume, which is area into height. Here I have the height term. So I will get the dHL by dt. So I'm going to substitute m here. And I already have the equation of qm here. And I'm going to get the height term. And going through this equation, after the substitution that we have, you're going to get dHL by dt. And by taking the integration, you're going to find HL. Okay, that's HL here. And as you find HL, you're going to substitute HL from here till here. And substituting it here, you're going to get the QM equation. And this is my QM equation. I got my QM equation that changes with time. So that is the QM equation that changes with time. Okay, how beautiful is that? Great, right? Now, I can also get something good about that out of that equation. Is that what? Now, if I want to calculate the time that it takes for this vessel to empty. When I talk about a vessel to empty, that means it started from an HL naught value. Okay, it started from a certain H naught value till my H is equal to 0. So that was my final value. And I already have the equation that I derived dHL by dt, in which I have HL is equal to HL naught. So if this HL is equal to 0, I'm going to get the time for that to empty. And that is the beautiful equation that I'm going to get for time to get empty. Now, if this was an open tank, for example, and this is open to atmosphere, so my gauge here is going to be atmospheric. And because my gauge is going to be atmospheric, if this was open, I could consider PG is equal to 0. And if I do this, I'm going to get this beautiful term that is very simple, which is the time taken for this to empty. So what do we have? These equations are just showing you how did I do the derivation. Don't worry about it. So I showed you now two things, right? I showed you the mass flow rate through a hole, and then how to calculate the mass flow rate of a liquid through a tank. And now we're talking about the mass flow rate, or the flow of liquid through the pipe. And talking about the pipe, so it enters through a certain location and then it exits, right? So this is like the downstream. This is the upstream. And down till here to the downstream. And as it enters, it goes from a certain diameter to a smaller diameter or a bigger diameter. So there's a friction here, okay? There's a friction here. There's a friction here. And actually there's a friction also with the sides. So there's another friction with the sides. There's a friction when it goes outside from a certain diameter to another diameter. So I have K for the entrance. I have another K for the exit, which is the friction loss. I have another K that is because of the sides here. I could have another K because of an elbow. Or it's not an elbow, it goes 100 degrees, okay? It's like you're driving, and while you're driving, you need to go to a roundabout. Definitely your speed would be much less if it was just an elbow, right? So all these are friction values. And actually those friction values are very important to know because they are the ones which cause the drop in pressure. And if I know the drop in pressure, you see here, like I know the friction values, I also know the drop in pressure, I can know how much is going to be spilled out. Okay, how much is going to be spilled out? Why? Because if I have a lot of drop in pressure, the amount to be spilled, that will be less. So if you want to talk about the flow of liquid through pipes, again we are going to go through our mechanical energy balance, and that we already said. Delta Z is equal to 0, Ws is equal to 0, and we are going to have simpler terms here. Well, one of the terms here that we want to consider is the F term. What is F? F is the friction loss. Okay, so F is the friction loss term. How to calculate friction loss? I can know what is the friction loss. I already know the velocity. I know GC. I need to find KF, which is the head loss. How to find KF? If you want to find KF, you need to find F, which is the fanning factor. Fanning friction factor. Come on, doctor, please make it easy. So this is how we need to know, right? You need to find friction factor in order to find the head loss factor, in order to find the friction factor. And if you find the friction factor, you just substitute to find the QM, okay? That makes it easier. Now the question, how to find this F? We have an equation for KF, right? It comes from here. But and we have an equation for F, right? So F is equal to KF into U squared over 2GC. We have an equation for F. We have an equation for KF, but we don't have an equation for F. How to find F? To find F, we need something called the roughness factor and the diameter, okay? And we are going to look at this just here, okay? What do we mean? E is the friction, the roughness factor. So if you're talking about a glass pipe, very smooth, the roughness is equal to 0. But however, with other kind of materials, pipe materials, the roughness is going to have a certain roughness. And this roughness means friction. And if we have friction, that means the mass flow rate that is going to be exiting from a system is going to be less. And how do we calculate this? Please help me. Now, because you have a small diameter, for example, it also could cause some kind of a friction. So what do? You divide the roughness over the diameter, over the internal diameter. So if you divide the roughness over the diameter, and if you know the Reynolds number, you can find the friction factor. And for example, just to take an example, so if the Reynolds number is 10 to the power 5, so that is my Reynolds number, okay, 10 to the power 5. And if I want to talk about 0.001 E over D, I found out that E over D was 0.001. So I went 0.001 here, that line, and I go up, 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 up. Here, it's crossed. So going cross like that, I found out, well, my fanning friction factor was 0.005. How beautiful. I found the fanning friction factor, which means I can find Kf, which means I can find F, which means I can find Qm. Okay, so now I'm just showing you how that develops one by one. Well, now, if you are not going to use this figure, your life is not going to be easy. Why? There are equations for this figure. However, what are these equations for this figure? If it's laminar flow, use this F. If it's turbulent flow, use this F equation. If it is a turbulent flow in rough pipes, use this equation. If we have smooth pipes, use this equation. If it's a smooth pipe with a Reynolds number less than 100,000, use that equation. And then a great guy, scholar Chen, he came up, said, stop. I want just one equation for all those equations. And he came up with a new one equation, considering some assumptions and some errors. But he came up with one equation. But believe me, why to go through all that? Just use the figure. Just use the figure. It's going to make your life much easier. And by the way, the equation you see here is written. Laminar flow, F is equal to 16 over Reynolds number. And all those complete turbulence, these are the other equations that I have here for the turbulent flow. So this guy made it easier, right? Okay, he made it easier for us. Well, what else do we have? Actually, we thought that Kf is only one Kf. But we thought that only one Kf is not only one Kf. There are other Kfs. Oh my God. So we thought that Kf is only that. No, there's another Kf. And this is the Kf of the entry, of the exit. And actually, there are many scholars, they made it easier for us. They said that we made an equation for you. And this equation that we made for you, Kf depends on two constants. If you know your Reynolds number, if you know your internal diameter, you can know your Kf. Okay, how can I get K1 and K infinity? So it told us, well, if you have an elbow, this is the K1 and K infinity. However, elbow with a long radius is 800.2. If you have an elbow of 45 degrees and a standard R over D is equal to 500.2. Well, if you have an elbow of 180 standard, it's going to be 1000.6. Well, it could be a T, or it could be a valve, or it could be a globe valve, a standard globe valve. And we are going to get the K1 and K infinity to find Kf. And by that, I'm going to get the Kf values. Well, there are other Kf values from entrances and exits as well. So if it's an entrance, okay, so if it's an entrance, my Kf value, if you can see here, it's written here, for pipe entrances, K1 is equal to 160 and K infinity is equal to 0.5. And for exit, K1 is equal to 0, K1 is equal to 0, and K infinity is equal to 1. So here I can calculate my Kf. So I'm going to calculate my Kf of entrance, my Kf of exit, my Kf of what kind of I have as a system, T, valves, globe. I'm going to sum of all of those Kf, sum this Kf with this Kf, sum all of them, and then I substitute it to find out what? To find out my equation, C0, to find the C0. Oh my God. To find out C0, okay? So this and that, sum all of this, considering all the head loss terms because of the entrance, because of the exit, because of the friction, the pipe, because of the head loss and the fittings, all of that is here, and we can get C0. But to surprise you, if you do this, and you know that the Reynolds number is not greater than 10,000, we already said that a rule of thumb, C0 is equal to 0.61. If you do your calculation after this whole long energy, you're going to find C0 is equal to 0.63. Okay, so sometimes experience helps, right? It makes your life easier. So if you want to do it the more thorough way, it depends on the question, or you just can take the assumption here 0.61 if you're, of course, you know that Reynolds number is greater than 10,000. Okay, so what is your solution procedure? Your solution procedure, if you're trying to solve a problem that you have here, the solution procedures is as follows. It starts with determining the mass flow rate of the discharged material of the system. To determine the mass flow of the discharged material from a piping system, first thing, you need to know information about your system. You need to know the length, the diameter of the system, and the type of pipe. From the type of pipe and the diameter, I can know what is E over D. And knowing what is E over D, I can know, of course, I'm going to get from the density and viscosity here, the properties of the fluid, I can get the Reynolds number. From Reynolds number and E over D, I can get F. And from F, I can get KF, right? And from KF, of course, I'm going to substitute to get F, and so on. So I need the information, and I also need the work input if I have a shaft work, but maybe I don't have any shaft work on pumps or turbines, right? And maybe I need to know the elevation changes. Maybe there's no elevation changes, so I'll put delta Z is equal to 0. So maybe here delta Z is equal to 0, and the shaft work is equal to 0, right? And I need to identify from which point I want to see at what point, because maybe these 2 points has no elbows between them, right? So I'm going to apply this mechanical energy balance on between these 2 points. And then I'm going to, of course, calculate my friction. I'm going to calculate my velocity. And after I calculate my velocity, I'm going to find my QM. Hold on, there's one thing. Maybe I don't have the velocity term. So what I'm going to do, I'm going to assume or guess a velocity term, okay? And if I assume your velocity term and substitute, of course, your friction factor and the excess loss, you're going to get the value here, the QM value, right? And actually, if you get a QM value, or the mass flow rate value here, maybe that goes to 0. But what I'm trying to say that if you calculate the QM value, maybe you need to repeat some calculations. Why? Because if you calculate the new U, you see the new U, which is QM over rho A, or you calculate your new U here, you calculate your new velocity here, maybe this velocity is different from your assumed velocity. So you need to repeat the calculation till you get your new velocity very close to your assumed velocity. And by that, you're going to substitute the velocity here to find the value of QM. So that could be an iteration of like 3 iterations to get your value depending on your initial guess. Great. So that is the procedure for what you're trying to go through solving. So that is part 1 of chapter number 4. I'm going to stop here at part 1 of chapter number 4 for liquids. Next time we're going to take the part 2 where we're going to talk about the flow of vapor through holes and then the flashing liquids and the pool of the liquid. So till then, all the best and see you in part 2 for chapter number 4. Thank you very much.